This is Himabindu, Assistant Professor in IARE College. So today in this video, I would like to explain what are the definitions in the finite automata. So what is meant by definitions of finite automata in the first unit? How many definitions are there? We will discuss on this video. So coming to the finite automata. So what is meant by finite automata? So define a automata. So it is a abstract model. So what is meant by automata? So it is an abstract model of digital computer. So we are designing a DAFA and NFA, and what are those in the sense? So those are the models which we are going to represent in a formal notation. So those models are named as a here automata. So those are represented in the abstract model. So it is an abstract model of digital computer. So it has a mechanism for reading input. So previously in the last videos we discussed about the construction of DFEs and NFEs and the push-down automata. So those are all the abstract models. So those named as an abstract models of the digital computers. And automata enables the scientists to understand how missions. So by seeing this one, so when we are giving one input to the machine, it will the string which is going to be accepted or rejected. So this information will be understood by the scientist how machine compute the functions and solve the problems. When we take the examples of Turing machine, so here in the Turing machines we need to construct, we are going to construct the Turing machine for the addition of the two numbers. So the addition, how this addition is going to be happen. So the entire process, when we give two numbers to the Turing machine, so it will give the result after the output. So that is entire process is named as the computation. So these models which are going to be understood by the scientist to compute the machines which we are going to use, machines or models which we are used as a computational functions. And what is meant by symbol? So here the symbol is the smallest building block. So here the smallest building block which we can be an alphabet or letter or any picture. So here while designing the DFA or NFA, so we are just taking the values like 0, 1 or A, B. So those are all the alphabets, so which are represented as an alphabet. So in this single values are named as a symbols. Single values are named as a symbol. So those are the smallest building blocks for the construction of automata. And what is meant by alphabet? So whenever how many symbols are there, those are all comes under to one category. Those nothing but alphabet. So they're named as a sigma. And this is the example of, this is defined as a sigma, and these are the examples of alphabet. So those are sigma, which is having the alpha number of symbols, those are represented as an alphabet. And coming to what is a string, mention an example. So what is meant by string? So till now we have seen a single value and multiple values of single, and with the combinations of these values we will form a string. So what are those in the sense? The string, which is a combination of alphabets. So many alphabets are there. Those are all the combinations. What are the possible combinations are there? Those are represented as a string. We will generally denote the sequence. So it is a finite set of sequence of symbols. So how we will denote the string in the sense? It is a sequence of a sequence of symbols. So like here it's a sigma, which is having the values of 0, 1. So with this 0, 1, what are the possibilities of the string? So how we can form the strings? Either it can 0 or 0, 1 or 1, 1 and 1, 0. And this is the 2 length, and we can also write the values of single length like this. And 1, 1, 0 and 101, and so many possibilities of the strings. So how we can form the strings in that sense? It is a finite set of sequence. So finite set of sequence are represented as a string. So this is about the string. And what is the length of the string? So how we will denote the length in the double bars. So here in between we will take the word w is the string. So how we will denote this string length in the sense two vertical bars. So those are and if you have the string value like a b b, so what is the length of this one? We need to count the strings. So string length 1 2 3 4, so equal to 4. That is how we are going to decide the length of the string. So this is the length of the string. And what is the substring of the string? So how we will denote the substring? So previously we discussed some examples, like we need to construct the DFA for this substring, like 01 substring. And if you, what is meant by substring? So it is a see any sequence of zeros or more. So any sequence, so either it can be epsilon or any zero, A or B combinations, or A B combinations, consecutive symbols of given string. So consecutive symbols of given string. Suppose here, so B is a substring. So what is the consecutive? So next coming, so suppose this is the string. What is the consecutive of this substring? In the sense, B is the consecutive string, or B consecutive symbol for the substring. Like this we will denote the substrings. And what define null string? So define null string in the sense, so empty string is a string which with zero occurrences of symbol. So null value is nothing but epsilon. We will denote this as the epsilon symbol. So here with this we can we have the values, and without input string also, if it is reaching the final state. So without input string also it is reaching the final state, so that represents the null value. And empty string is a string with zero occurrences of symbols. So here if you observe this finite automata, in this one there is no occurrences of any alphabet, only null value. So that null value is also having the finite automata, so this is also acceptable. What is a prefix of a string? So prefix and suffixes. So here prefix in the sense left hand side part, what is there for the any string, we will call it as a prefix of the string. Suppose here this is the entire string. So prefix in the sense the left hand side. So whatever there in the left hand side. Suppose this is a ABC is the ABC, or AA, BB, and CC is the example for this one. So what is the suffix? So prefix of the string. So here the what are the prefixes? So here the prefixes, we can name it as this one, or we can also name it as this one, and this one, and this one. So these are all the prefixes of this C. So prefixes of the C. So here, and also we have the sigma also prefixes. So this is about the leading symbol. So leading symbol of string is called the prefix. What is the suffix of the string? So what is the suffix of a string? We will trailing. So trailing symbol. So that means prefix opposite suffix. So here after the string A, B, C is there. So here what are the suffixes of the string? Suffix in the sense. So this is the initial value and suffixes. After this substring, whatever there, we will name it as a suffixes. So what is a proper prefix and a string? Proper prefix. Proper prefix in the sense only the value. So after the substring, whatever there left, we will name it as a prefix or suffix. So prefix in the sense, left hand side part what is there, we will name it as a proper prefix. So here example. So here ABC is as an example. So with this one, so what is the prefix value? for the C. So prefix value is AB or E or epsilon. So with excluding this C. So ABC excluding. And proper suffix. Same thing, we will represent the, so ABC as a string, we will exclude that string and this ABC. So suffix in the sense after this one, B or C and epsilon. So these are the A, B, C. And next, the power of an alphabet. What is meant by power of an alphabet? So here the power in the sense, we are taking the value of one or two input symbols. So power in the sense how many times iterations, we can exactly say that it is a iteration. So what is the power and alphabet? Here P is the value, so P is an alphabet or sigma. So over 0, 1 are the symbols we have. So those how to represent those power of P1. So sigma 1 or sigma 2 and sigma t. And here 0 elements, so sigma power 0, no symbols are there, so that we will represent only epsilon. And 0, 1, so here power 1 represents only the single values are there, 0, 1. And 1, 2 in the sense the length of the sigma's 2 is nothing but the length of the string is the 2. So what are the possibilities of the string length 2, all will written like this. And the 3, so power of 3 is equal to 888, 000, and what are the possibilities of the length 3? We will write the values. We will write the strings like this. So these are all the power of an alphabet. So what is meant by power? So here whatever the input symbols are there, so for that one we will give the iterations. So whatever the number is there, for that length of the string is that number. So that we have to choose all the possibilities of the string from the input symbols. So what is meant by clean closure? So clean closure is nothing but, so till now power set we have seen, so that here clean closure will represent the sigma star. So that represents all together, what are the power set is there, so all together we will represent as a clean closure. That means we will be sigma 0 and sigma 1 and sigma 2 and sigma 3. So what are there? We all together combine and we will name it as a clean closure. And next one, what is the positive closure? So positive closure, here we are including the P naught. So what is the difference between positive closure and clean closure is nothing but, so here in the clean closure we are including the epsilon symbol. Suppose here epsilon is there and union 0, 1 and 0, 0, 0, 1, 0, 1, 1. So here epsilon is included in the clean closure. But coming to the positive closure, we are excluding this epsilon. Remaining all together we will write. So here we will represent as a sigma plus, and here excluding this P naught, we will write all the values here. That is the positive closure. And define a language. So till now we have seen the strings. So what is meant by language? So language is a set of strings. So till now we have discussed the prefixes, suffixes and strings, how we will form the strings and what are the properties we have seen. But here the language is nothing but it is a combination, it is altogether a set of strings are named as a language chosen from the P star. P star is nothing but a clean closure of one sigma. And a language is a subset of P star. So P star, so in this one, P star is nothing but, so it is a subset of, so language is a subset of, so language is a subset of clean closure. So clean closure. The language which can be formed over the P can be a finite or infinite. So the language what we are forming with the P epsilon symbols, those are named, it is a infinite or finite. And language that contain the strings. So what are the strings with the A or B? So here we have taken the sigma as a comma B. So with that, what are the possibilities of strings we can form? We will write all together as a language. So here P is equal to, sigma is equal to A comma B. So P is equal to A comma B. So whatever there with the sigma, so here the star, so epsilon, A, AB, and so on, we will write together. So that is nothing but. So what is the grammar? So grammar is nothing but, so it contains a set of rules. So here we till now we have discussed the symbols and symbols, alphabets and strings, and now languages. So these are the hierarchy. So these are the hierarchy. So after this one, we form the language. In this one, we have to maintain some rules. So set of rules will generate the grammar to generate the strings of a language. So grammar is nothing but in the language, we will set some rules to produce the grammar. And next one, define formal languages. So formal languages, so is a set of all strings which are where each string restricted. So each string restricted over a particular forms of a string. See, a string with given input. So formal languages are a set of strings. So for every language we have multiple languages in the finite automata. So here, coming to the finite automata languages, we have four types of languages. One is a regular languages, and second one is the context free language, and third one is context sensitive, and fourth one is recursive enumerable languages. So these are the four types of formal languages we have. So here, set of all strings where each string restricted over particular form. So for every language, so whatever we are telling that in a finite automata we have four languages. So every language is different from one language to another language. So where each string restricted. So in every languages there is a string restriction in a particular form. So that's why we have a four types of languages. So those are the four types of languages, and four types of automation. So automation is nothing but how we will form the machines with these languages. Those are named as a finite automata. So types for how we have four types of automaton. One is a finite automata, which is related. We can construct the finite automata with the language regular, finite automata with the regular languages. And push down automata, we will construct the push down automata with the language, context free languages. And linearly bound automata, we will construct the linearly bound automata with the language, context sensitive language. And Turing machines, with the Turing machines we will construct with the recursive enumerable language, we can construct the Turing machine. So these are the four types of automata. And what is the finite automata? So finite automata, so an automata that accepts the regular languages. So here we have four types of languages, formal languages we have. For that one, we have four types of automaton. In that one, first one is a finite automata. So finite automata is nothing but which accepts the regular languages is called a finite automata. So what are the types of finite automata? So we discussed about the finite automata. So finite automata, we have the two types of finite automata. One is with output and without output. So here with output we have two more missions, Moore mission and Millet mission. And here we have three types, DFA, NFA and epsilon NFA. So here totally we have five types of finite automata, and in this one deterministic finite automata and non-deterministic finite automata are both equivalent in power. So here, and what is meant by push down automata? So push down automata that accepts the language context free languages. So context free language is called push down automata. And types of pushdown automata. How many types of pushdown automata we have? Deterministic and non-deterministic pushdown automata. So coming to the deterministic and non-deterministic. So for this one, we will take example of W and W reverse. So this is a non-deterministic pushdown automata. And what is this W in the sense? It is a string. So WR is nothing but W reverse, the string reverse. So here taking example 0110. So this is the W and this one is the reverse of that string. So when we write, we don't have anything in between W and W reverse, we can name it as a non-deterministic pushdown automata. And deterministic pushdown automata, so when we have the value like no determinism is there, so non-determinism is there, we will represent as additionally we will add the symbol C. So this is also 01 C10. So if it is in the form, we can say that it is a deterministic pushdown automata. And what is a linearly bound automata? So linearly bound automata with the languages, context sensitive languages, we can form this linearly bound automata. And in this one, we have two types of automata. One is a deterministic linearly bound automata and non-deterministic linearly bound automata. And what is mean by Moore and Millet mission? So previously we discussed, so finite automata we have with output and without output. In this one with output we have a Moore and Millet mission. So Moore mission is output depends only on the current state. So here let me draw the Moore mission and Millet mission, then we will discuss. So Moore mission, the state itself, it is having the output here, and if you take two states with the two input symbols, two outputs, and with the value a single value, and here. So this is a just example of Moore mission. So Moore mission, so in this one, this is the state, the current state. So the output depends only on this is the output. The output depends on the only current state. So same state in the current state. So it does not depend on the current input. So it is not going to be depend on the current input. Define Millet mission. So Millet mission is the state. If we have the same, and we will represent the value with the input and output. So with the one input, and also we will represent in the same transition, we have to represent the value of output also. So this is the input and this is the output. 0 B. So this is the input and this is the output. So here if you observe both diagrams, the Moore mission, this is Millet mission. So in these two diagrams, those states, the state itself, it is current state itself, it is having the output symbol in the Moore mission, And Millie mission, the state in the transition, it is having the input and output values. So Moore and Millie missions are different. And what is define a finite automata? So a finite automata consists of finite set of states and transitions from state to state occur and input symbols chosen from the alphabet. So here, if you have a value of, if you have a language, regular languages, we need to construct a finite automata. How we are going to view the finite automata transition? So here this is the input and this is the finite FSM, finite state machine, and we'll give the input accept or reject. So here with this, for this input, when we give input to the machine, and it will either accept or reject. So we have only two states here. And what is meant by what is the initial state? So here, while constructing any DFA or NFA, we require the initial and final states. So here, so this is the initial state. The Q naught generally will represent the DFA or finite automata with the Q naught as an initial state and QF as a final state. So representation, the initial state will have the initial arrow mark, and the final state will represent the double circle, and it is a starting state from which reading an input string from the string starts. So here onwards we need to start. So here only we need to give the initial value, initial input symbol to this initial state. And what is the final state? So final state is a, so final state, it is a so it is whenever we are giving the t a value 1 as an input symbol, it is reaching the final state. So finally, when we reach the end of the string, it should reach the final state. So that is nothing but we have to represent the two circles representation for the final state. So these are all the examples of these are all the definitions what we have in the finite automata. So here, so finite automata, we have initially we have the values. Initially we have the value sigma, symbol and alphabet, and symbol, alphabet and string. With the alphabets we can form the string, and in the strings we have a power of the string, we have the power of a sigma we have, and we can form the languages with the multiple strings. And how many automata we have? Four types of automata. So we have a finite automata with the two types. One is with output and without output. In this one, Moore and Millie mission, DFE, NFA and epsilon NFA. So for every finite automata, we have a different values, different transition functions here. And how many types of finite automata without output? Moore mission and Millie mission. And how to design the finite automata, initial state and final state. So these are the finite automata definitions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.